Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here with Priyank Shukla from Synopsys, who's going to talk today about next-generation SerDes. Priyank, what is a SerDes? What's a brief description? Obviously, it's used in almost everywhere that we have computers these days, but what exactly is it?
So SerDes is a serializer and deserializer portion of a circuit where you transmit data from one chip to another. So there is a way of transmitting data from one chip to another in a fashion where it's first serialized, sent to the channel, and then to the second chip, and then deserialized. So the portion of circuit that does this part is called SerDes.
And how is this changing? What's the problem that has to be solved?
Right. So as we see more and more disaggregated computing, so computing is happening now across different chips. So there's a processor which computes, and there is an accelerator that does other part of compute. So there's a need of data transfer between these two chips. And the bottleneck now is the speed of this data transfer. There are different interconnects here, and Ethernet is a de facto interconnect when you're going from one rack unit to another rack unit. And there are different data rates of Ethernet, and they come up with their own pros and cons. And the next generation designs is putting a lot more constraint on how those SerDes are designed.
Let's drill down into this.
Sure.
Priyank, what are we looking at here?
So we are looking at a hyperscale data center, how the guts of hyperscale data center looks, and what are the trends of interconnect at the data center. So at very high level, data center is a rack and rack of accelerator and servers, which are connected together with different interconnect. So let's start bottoms up. So what I show on the left side here is one rack unit, which sits in a server rack. So this is a server rack. First thing here is a rack unit. This is a 19-inch pizza box, which is a basic fundamental unit of a server. So this rack unit would have CPUs to process, accelerator to offload the work or task from CPU so that they can process it faster. And then the CPU and accelerator are connected to other CPU and accelerator through a network interface card or NIC. These days, these NICs are becoming smart NIC because they also have a lot of data processing capability built in. So all this together is one rack unit of a server. So here between accelerator to CPU and CPU to CPU, the dominant interface is PCIe. So PCIe is seeing its transition from Gen 4 to Gen 5 to Gen 6 now. And for NIC, we are seeing the Ethernet cables or Ethernet data rates moving up. So that Ethernet brings us to the next part of this interconnection, which is box to box, or this rack unit to rack unit. So within a server rack, you will have multiple rack units, which are connected using cables, which are direct attached copper. So these are copper cables, which are typically 1 to 3 meter long. So these were previously 25 Gbps Ethernet. Now they are moving to 100 gig Ethernet. Some of the hyperscale data centers have skipped 50 gigabit deployment in between, and they are moving directly from 25 to 100 gigabit Ethernet. And there are a lot of discussion today whether this interconnect should be cable or electrical cable, or it should be optical cable. So there's discussion about DAC or optics for this connectivity. But one thing that's common here, it is 100 gig SerDes. So within a rack, there are different rack units which are connected with 100 gig SerDes. So let's look at within data center connectivity, where you have multiple racks connected through different levels of switches. And here you have top of the racks connected to leaf switches and spine switches. Here, Ethernet is the dominant interface, and the SerDes unit is 100 gig Ethernet, but there are different aggregated bandwidths or different port bandwidth, which are moving from 400 gig to 800 gig. IEEE has constituted a beyond 400 gig study group, and that's working on defining next data rate for this Ethernet. But today, 800 gig Ethernet is available from Ethernet Technology Consortium, and we are seeing this socket moving really fast in the terms of bandwidth demand. But the basic fundamental unit here is 100 gig SerDes, which aggregate to provide this 400 gig or 800 gig bandwidth. So 400 gig ecosystem is currently getting shaped, and there are higher demand for 100 gig SerDes than ever before.
We're starting to architect these systems around massive amounts of data. It's been increasing on a regular basis, but now it seems to be skyrocketing And it's not just in the hyperscale data centers anymore, right? The cloud, it's now in these data centers that are being built out from the edge. So on-prem versus off-prem type of applications.
Right. And that brings us to the requirement of connectivity between these different kinds of data centers. And that's where switches come into picture. And you need very high bandwidth and high radix switches to connect this data center effectively with low latency links for high performance delivery of artificial intelligence, virtual reality services. So this shows the progress of switch roadmap with respect to time. So last December, 25 terabit switch, which is actually 25.6 terabyte switch, for top of the rack switch implementation was made available for switch implementation. So this uses 400 gig Ethernet port, and the SerDes unit is 100 gig SerDes for this one. So this silicon has 256 lanes of 100 gig SerDes integrated in this. Next upgrade of this switch family is going to be 50 terabit switch. And if it were to be implemented using 100 gig SerDes, one will have to implement 512 lanes of 100 gig SerDes in one die. So that's a really, really complicated problem to solve. And this is putting a lot of pressure on the way SerDes IPs are designed or integrated in these kinds of highly dense SoC. So there are new set of requirements which have emerged to address these kinds of switches. Let's talk about those requirements. So I talk about placement aware architecture here, which is a requirement from the customers who are integrating so many lanes, because they have to not only integrate these lanes, but also escape all these high-speed lanes in a package, let's say 6-to-6 package or 7-to-7 package. So unless the bumps or the IP are not designed properly, there would be interference tolerance and jitter tolerance between the lanes, because you're integrating so many lanes on one die. So there's a need of a placement aware architecture so that it allows the reference clock to be routed in such a dense integration. Second, these kind of switches interoperate with multiple channels. This could be placed very close to a pluggable optics. This could be placed with a copper backplane channel. So the performance of SerDes across channel needs to be uniform, and it should be power optimized. So there's a requirement from SerDes that it works best in class way across the channels. Finally, these switches are used in hyperscale data center, where even a second or a microsecond of downtime creates havoc. So there are a lot of preventive software, maintenance software that run on this system. And if this switch can provide some intelligence or some sensor data to those preventive maintenance software, it helps the hyperscalers a lot to have a robust system. So there are a lot of diagnostic features which our customers have started asking, such as non-destructive iPlot. So a non-destructive iPlot shows the performance of receiver on real time. Using this data, the hyperscaler software can figure out how a particular link is performing. And if it's needed, the link can be reset on a downtime so that there is no performance degradation. And finally, there are temperature sensors which are required in this IP, because these are huge dies here. So the temperature cooling is done based on different zones. So if these kind of SerDes IPs have temperature sensor inbuilt, the temperature can be maintained and the performance and power both can be optimized. So these are new requirements which you have seen for 112 gig SerDes with respect to switch architectures in last 2-3 years.
And what's going on here is we're trying to solve the bottlenecks for moving all this data around. So you're seeing more in memory type of computing architectures that are starting to develop. You're seeing more processing that's going on even at the endpoints. And now what we're starting to see is let's increase these pipes and be able to move this stuff through at a very fast speed, right?
Yes. So moving this data through pipes is done using NICs, network interface card. This is how this data from switches go to a rack unit. And as the switches go with their optic cycle and Ethernet is being deployed with 400 gig Ethernet, we are seeing next generation NICs being designed today. So in market, you will find 200 Gbps NICs available today. And the new designs are starting with 400 Gbps. So these 400 Gbps NICs will have multiple form factor or multiple modules. One of them is QSFP-DD, and also QSFP 56 and also OSFP. So the new designs of NIC has to support all this different module form factor. But one thing which is common for this next generation design is this 100 gig SerDes. And NICs, if you see, as you said, works as a pipeline between 2 points or 2 chips in this processing function. So PCIe has to be interfaced with high-speed Ethernet links here. So as the SerDes goes to 100 gig from 50 gig, the PCIe has to go from Gen 4 to Gen 6 to support this throughput in this pipeline. And finally, there are different form factors which are being deployed today with the NIC. So PCIe and CHEM form factor was the dominant in the previous generation, but Open Compute Platform has come up with OCP 3.0 form factor, which has started seeing traction here. So a lot of new designs are trying to address this OCP 3.0 form factor. And these changes require some new features from 112 gig SerDes. Let me talk with you about some of those which are specific to this NIC application. So first is this form factor, QSFP-DD and QSFP56. So if a design has to be backward compatible, these NIC design has to support all these form factors which we were talking about. So to support that, a link has to support lane reversal. Multiple lanes make a link, and the requirement is different lanes can be connected to different links and would support lane reversal. That TX can be connected to TX3 of different lane and TX2 can be connected to TX4, any of these. Then there is polarity inversion, where a TX plus can be connected to TX minus in this kind of NIC application. And finally, the requirement is lane swappability, meaning between 2 links, you want a feature where link 1, lane 1 can be connected to link 2, lane 2, and it still works as one macro. So these put very complicated requirement on the design of SerDes. When you design a macro, you need to ensure all these features can be supported so that this NIC can support backward compatibility between QSFP56, QSFP-DD, and OSFP. Finally, this NIC support multiple generation of Ethernet. So before this, there was 100 gig Ethernet, there was 40 gig Ethernet, 25 gig Ethernet, and the way the speed is determined is using auto negotiation and link training. So the new generation 100 gig SerDes with their soft logic has to auto negotiate and train its link with multiple generation of Ethernet. So a lot of verification and interoperability requirements have come up. So it's required that the auto negotiation and link training is incorporated in SerDes. And finally, extra long reach SerDes requirement. So when OCP started CEI 112 gig long reach, they defined some specification for 112 gig SerDes. But in real data center applications, we are seeing customers are asking about 40 or 42 dB of channel loss to be supported with this SerDes. So that's a new requirement on 112 gig SerDes because the NIC has to support different channels. So these are the new requests for 112 gig SerDes based on next generation NIC architecture.
You've got a number of things in motion here, one of which is the standards themselves are changing. Not everybody is doing every upgrade of every server at the same time and all the SerDes that go into them. And then on top of that, your data movements are very specific depending upon what's happening within any particular company at any particular moment, right?
Yes, and that's put new requirement on the way data is stored. So data is stored traditionally as an SSD using flash storage, solid state drives. And PCIe was adopted with SSDs in about 2014 to 2015 timeframe. With the PCIe switch, the SSDs were scaled within a rack. So multiple rack units using PCIe as an interface can be connected together, and processor can use all this storage as a server storage and can directly map using firmware memory registers. But now with Ethernet 112 gig SerDes, NVMe over Fabric is being deployed. So this gives ultimate scaling to the SSD storages. So now with the NVMe over Fabric, the storage is not limited to one rack unit, but you can have farms and farms of storage, which will become a fabric through this Ethernet, and those can be addressed directly from a processor. So now the sky is the limit with the SSD storage and the server farms. So NVMe over Fabric SoC is the next generation SoC design we are seeing with the traditional SSD companies. And this also needs an Ethernet PHY here, 112 gig SerDes PHY, but also PCIe PHY. So the requirement from these customers is 112 gig PHY, but they are asking for some new features which were never asked from these kind of 112 gig PHY. For example, they are asking for interoperability with 112 gig SerDes and PCIe Gen 5 and 6, because these two will be on the same SoC. And that's where PCIe SIG becomes important. So if you are part of PCIe SIG interrogators list, it makes sure that these kind of next generation SoC works across the ecosystem. So it's crucial that you have a version of PCIe PHY as well as Ethernet PHY that can be seamlessly integrated in next generation NVMe over Fabric SoC. Finally, these SSD vendors have to work with one of the most difficult channels in data centers, because once they design their product, they don't know which servers they are going to get plugged into. So they have to do interoperability, and they have to do multiple times power up and power off cycles. So they're asking us repeatability of adaptation coefficients. Meaning if the SerDes is turned on and off, let's say thousands times, how does SerDes behave? Does its adaptation coefficient, does its performance change? So that's a crucial parameter for them. So this is asking us very new questions which were never asked. So there are some changes or some optimization in 112 gig SerDes which is needed for this. Finally, SSDs come up with the new form factor. Solid state drives very rarely use PCIe form factor. They use U.2 and U.3. And there are a lot of customizations with the SerDes PHY implementation which are needed in terms of digital implementation to support this U.2 and U.3. So this requirement was never there for Ethernet PHY, but these new designs are asking 112 gig PHY also to support U.2, U.3. So these are new requirements with respect to SSD applications with hyperscale data centers.
So given all of this, what happens on the SerDes architecture itself? How is this changing?
So now is the time where you need a SerDes that does this equalization by balancing analog as well as digital signal processing. So analog and digital signal processing both offer excellent merits, but it's very important that these are balanced. If digital signal processing is the only implementation option, you run into a lot of latency issues, and the performance and implementation doesn't become a competitive implementation. So you need an architecture for best performance across channel. I'm showing here different channels for hyperscale data center. There are orthogonal channels, there are cable backplane channels, and there are different versions of it. So these are the channel S parameters as submitted at IEEE and OIF, and this shows wide variety of performance of different channels. So there's a requirement that the SerDes performs best in class across all these channels, across frequency ranges. So with this, you need to have analog optimization in addition to best in class digital signal processing. For example, the transmitter needs to ensure that the lowest power is met with full 1.2 volt design. So this needs a lot of design innovation in terms of implementation of 1.2 volts in a complex tech SoC. And also there are a lot of non-ideal packages. So these days the package is adding as much cost as a die, because these are very complicated package. As I mentioned previously, they are integrating 256 or 512 lanes. So the SerDes by design has to ensure that the non-ideal packages can be compensated with added equalization. Coming to a receiver, this is what I was highlighting previously. If all the filtering is done digitally, so it adds latency in the data path. So there's a fine balance that needs to be done on analog, because analog does real-time processing. It doesn't add latency. Also, there are requirements with respect to bring up of these SerDes, because these are used with SSD these days. And this also calls for a balance between analog and digital implementation. And there are different channels, as I mentioned here. So to get best performance across these low loss and high losses, we need to have a lot of adaptation loop. For example, in the ADC, their resolution, their voltage scaling can be changed based on the channel only if you have deliberately thought it through in the design and it's architected to work across channel. Finally, the reference clock routing and reference clock forwarding is a crucial parameter which needs a careful design by balancing analog and digital implementation. So the next generation of 112 gig SerDes to address all these challenges needs to do this fine balance between analog and digital equalization.
So not only are you dealing with more data, you're dealing with more different types of data, and all of this stuff has to be moved with the same kind of integrity as you've done in the past, right?
Precisely.
What does this look like in terms of how they perform in different kinds of architectures?
Yeah, that's a very good question. So let me show you silicon results from our 112 gig SerDes. So this shows the performance of SerDes in a loopback channel. So we have transmitter transmitting at 112 gig, and it goes through 45 plus dB of channel loss and comes back to receiver. And here I show value of different blocks within the signal chain. AFE is analog front end, and you have ADC, and after this you do all the digital processing. So here I show how data is processed by balancing analog as well as digital signal processing both ways. So with 45 dB channel, you have analog front end doing its job by adapting based on the channel, and the ADC is performing highly linearly, and you see the discrete levels here. So this adaptation can be completed because we have firmware loops and the raw PCS algorithm to ensure fine equalization balance between analog and digital. And this is the ultimate result of all this. With the 45 dB of channel loss in the loopback, you set pre-FEC. FEC is forward error correction, which is defined by IEEE. So this shows the raw phi bit error. The spec here for long reach performance is 10 to the minus 4. So here we show 7.5 into 10 to the minus 6, which is 2 order of magnitude better performance with 45 dB of channel loss. And FEC is a way of improving this bit error rate by digital error correction. We have on-chip FEC, so we can demonstrate the performance after FEC using our silicon. And this shows post-FEC bit error rate of 0. So this SerDes are running at 100 gigabit per second, and we have let this SerDes run overnight. So it has transmitted more than 100 petabyte of data, which is more than the whole Netflix data. The whole Netflix directory is 100 petabyte, and there is no bit error done by transmitting that amount of data. So that's some solid performance across 45 dB channel. And this was possible because we have optimized both analog and digital performance.
You've got a lot of different pieces here. How do they all get integrated in a system?
Successful integration is highly, highly important these days because all our adopters have a solid time to market requirement that they need to have a successful product at one time. And a lot of them are using PAM4 signaling scheme for the first time. They're used to integrating NRZ signals. They're used to designing their package and all the digital simulation with NRZ. But there are a lot of new know-hows that they need to be made aware of as they are moving for PAM4 signaling. And successful 112 gig IP integration needs a design partnership at each stages of SoC development. For example, synthesis, constraint, and static timing analysis, because you have PCS and MAC, a lot of digital blocks working very closely with this hard macro or the SerDes. These integration needs to be flawless. You need to have test benches to find all the bugs for power format, clock domain crossing, and reset domain crossing. So these test benches need to be provided at the right time and should be exhaustive. Finally, reference clock forwarding was one point I was talking about previously for dense integration. So you need a thorough study here, and it's a different skill set. This is not an ASIC design exercise. This is package design expertise. So you need multiple teams to work together to provide a successful design integration experience for SoCs. Finally, testability is something that doesn't get talked a lot, but with PAM4 signaling, there are new test challenges because the transmitter is going to transmit a PAM4 signal. So how do you ensure all the test parameters for your test scan, at speed testing are met with the previous generation NRZ architecture? So a lot of time has to be spent in defining these requirements and making sure the customer does that integration on time. Finally, on the support, when such a complicated IP has to be integrated hardware support needs to have prototyping kit so that the firmware can be made available as soon as the design teams have started working. And the learnings from previous tape outs needs to be rolled into the future tape out so that the bugs are not reported. So the IP vendor for PAM4 IPs, support and integration reviews based on the previous experiences a must have. PCBs are going to see 112 gig PAM4 signals in very dense implementation for the first time. So an exhaustive package substrate designs study is required. So it's just not an NRZ signal which is getting integrated. There are new interference tolerance requirements which have come up now. So these are new support requirements on top of IBIS AMI model for effectively performing channel simulations here. So the support requirements for on-time performance of the design teams is very, very crucial these days, especially with PAM4 signal. So you need to have a successful IP integration with integration and support throughout your design cycle and after with the silicon bring up as well.
Priyank, what you've shown here is that it's not just about we're going to develop the fastest processor anymore. It's a lot of other pieces that go with this, right? All this has to be integrated. It has to be integrated with other systems. It's got to be designed so that you have some headroom going forward because not all the pieces move at the same rate.
Exactly. And it's very important that the basic pipelines of this connectivity, which is SerDes, works perfectly well across channel and provides the best-in-class performance.
Priyank Shukla, thanks for a great explanation.
Thank you so much.